Welcome to Chapter 5. Today we want to talk about area approximation, and we're also going to talk about sigma notation, Riemann sums, and I'm going to show you an applet you can use for your homework. So suppose we want to approximate the area under this curve here from A to B. So we want this area right here. One crude way to do that would be to find a point halfway between A and B, compute the height of the function at that point, and take that as the height of our rectangle, and the width of our rectangle will be the whole interval from A to B. So we'd be approximating the area under the curve with the area of that rectangle. And that's what you see here, f of C1 times B minus A. A slightly better approximation would be to cut the interval from A to B into two intervals of equal width, delta x, and compute the height of the function halfway through the first interval, and take that to be the height of the first rectangle, and then compute the value of the function halfway through the second interval, and that will be the height of the second rectangle. And so you would get, for your area, f of C1 delta x, that's the area of the first rectangle, and then you'd add on the area of the second rectangle. Now, there's nothing to say you have to use midpoints as the height of each rectangle. In these two pictures, I'm using left-hand endpoints, and I'm using 4 subintervals. So notice the height of the first rectangle here is 0, because that's the value of the function on the left side. And over here with the right-hand endpoints, the first rectangle doesn't have 0 height, but the last one does. And so we'll do an example of that right now. We want to divide the interval from 0 to 4 into 4 subintervals of equal width and approximate the area under F using left-hand endpoints. So in this case, delta x is going to be 1, because we want 4 intervals of equal width, and our whole interval goes from 0 to 4. These are our 4 subintervals, and we'll take the height of the first rectangle to be the value of the function at the left-hand endpoint. That's 0. So that's called a degenerate rectangle. The height of the second rectangle would be determined by the value of the function at the left-hand endpoint of the second interval, which is 1. So that height is 6. So the second rectangle has height 6. The third rectangle has height 12, and the fourth rectangle has height 12. So we can approximate the area under the curve by the area of these 4 rectangles. So 0 times 1 plus 6 times 1 plus 12 times 1 plus 12 times 1. And that would be 30. The next 2 pictures you'll see are me approximating the area under the curve using right-hand endpoints and using midpoints. And we'll see in a minute that this area approximation is the same as the last example. And then this one, we get 33. So let me show you the app that gives you that. And again, there's a link to this in your homework in the problems that require Riemann sum calculations. So up here, you'll see your function. And so you're going to change that to whatever function you want. I'm just going to leave it as it is. And then you set your left-hand endpoint and your right-hand endpoint to be whatever it should be. And then you can set the number of intervals you want. That would be the number of rectangles you're going to get. And this is a case where more is better for approximating areas. And then finally, you're going to set whether you want left-hand endpoint, right-hand endpoint, or midpoint with the value of C. And the instructions are right there. And then this last box here gives you your actual answer. Now, the red rectangles, I'm going to explain on the last page. But basically, these are getting counted as negative area, and green is getting counted as positive area. And so for our example, I've already plugged in the function, the left-hand endpoint, the right-hand endpoint, 4 intervals. And for midpoints, C equals 0.5, you can see that we get an approximation of 33. And then for right-hand endpoints, we get an approximation of 30. And whether or not I use midpoint, left endpoint, or right-hand endpoint, the area approximation will get better as I increase the number of rectangles. So that brings us to sigma notation. We want to add together a bunch of numbers. And using ellipses, that's the 3 dots there, is very clunky. So what we do is we write that sum in what's called closed form, and that is sigma notation. So this big thing that looks like an S is a sigma, and K goes from 1 to N. That means you're going to add A sub K, that's a formula, for K going from 1 to N. And there's nothing special about K. You could use J equals 1 to N of A sub J. So let's just practice doing this, write without sigma notation and find the sum. So this is equal to, when we put k equal 1 in, we get 1 squared plus 1. And then we add on the value when we put 2 in. So when we get 2 in for k, we get 2 squared, which is 4, plus 1. So this is k equal 1. I'm going to write underneath just so you know where that came from. This is k equal 2, and we're adding. Then we add on the value when k equals 3, and that would be 3 squared, which is 9, plus 1. And we add those numbers together because we want to stop at k equals 3. And when we do that, we get 17. So that's the sum. Okay, next one. When k is 1, the formula reads 3. Then we add on the value when k is 2, which is 3. This is a tricky one because it's so easy. There's no k in the formula, so you're just adding a constant 4 times. This is k equal 4, you get 3, and so your value is 12. And so we have some rules for finite sums and some formulas, and here they are. We'll talk about these in example B below. Those are called the linearity properties, and these are just a few formulas. We just did this one actually, the sum of a constant. We did the sum k equals 1 to 4 of 3, and the formula says that should be 3 times 4, which is what we got. We're going to look at this one in the next example. So let's use that formula. I'm jumping down right here. Let's use that formula to find the sum of the integers 1 through 20. And so let's write that first in closed form. That's the sum k equal 1 to 20 of k. And so our n in the formula is 20. And so using the formula up above, we get n, which is 20, times n plus 1, which is 21. And we divide by 2, and that gives us 210. So that's a quick way to add up some integers. Okay, next example illustrates the linearity property. By the first property in this box above, we can expand this single sum into 2 sums. K equals 3 to 10 of 3ak plus the sum k equal 3 to 10 of 2bk. Then using the second property, you see, you can pull the 3 out and you can pull the 2 out, just like with derivatives. So this is 3 sum k equal 3 to 10 of ak plus twice the sum k equal 3 to 10 of bk. But we're given this number and we're given this number. So this is 3 times 2 plus 2 times negative 5. So that gives us negative 4. I want to give you a preview of the next section and talk about integrals. Suppose you got a curve and it doesn't necessarily lie above the x-axis. It might go above and below. And you want to compute the signed area under the curve. And by signed area, I mean anything that goes below the x-axis is going to count as negative area. Anything above counts as positive area. So I've put the positives in green and the negatives in red. You can partition the interval from A to B into subintervals. So each of these has width delta x. And then supposing you pick a test point, C1, from each subinterval. Now, that doesn't have to be a midpoint. I've drawn it so it's midpoints, but it could be any random point. So this would be C1. This would be C2. And the height of the rectangle is going to be determined by the value of the function at that point. So the area of rectangle 1 is f of C1 times delta x. The area of rectangle 2 is f of C2 delta x. Down here, when f of Cn is negative, then what this is, it's negative the area of the rectangle because the height is going to be a negative number. Now, if you add all those numbers up together, you get what we call a Riemann sum. And since it's a lot of adding, we like to use closed form with a sigma notation. The sum I equals 1 to n of f of Ci times delta x. And if you use infinitely many rectangles, that's what we call the signed area underneath the curve. The true area underneath this curve, counting green as positive, red as negative, is called the signed area. And in the next section, we'll see that we call that the integral from A to B of f of x dx. So we don't use the sigma notation anymore. When we take the limit as n goes to infinity, so we take infinitely many rectangles, we get what's called an integral.